Hello everyone and welcome back to Networks class. Last time in class we discussed an example of Bender's decomposition. So we saw how that algorithm worked in terms of generating inequalities to add to the partial master. And then at the end of class we started talking about the max flow problem. And we just saw a few definitions to get us started. And particularly we got as far as defining the residual graph of a particular flow. And the plan for today is to continue talking about max flow. So we'll start out with a few more definitions that will explain a little bit more intuition about that problem. And then we're going to get into looking at the dual of the max flow problem. At the end of class today, we'll just start talking about an algorithm for solving max flows. So we're not going to actually get to do an example of this algorithm, but we'll at least be able to describe it today. So let's start with just the max flow dual and some of the material for today. So first we'll begin with a couple of definitions. So we'll define for a graph G and two nodes S and T. An ST cut is a division of the vertices in two parts such that S is on one side and T is on the other. So just to be a little bit more succinct about this, typically an ST cut is denoted by a pair of a set S and a set S complement. So the upper bars here just mean capital S, and that's to distinguish it from my lowercase s, which means the node. And S upper bar union S upper bar complement is just the whole set V. And of course, they're mutually exclusive, so no vertex is in both of these. So S intersection S complement is the empty set. So it's really just the complement of S here. And in terms of a picture to kind of visualize what an ST cut is, imagine that we have a graph like this. So it has some edges here. Maybe the edges look like that. And so here is an ST cut, or a visualization of the ST cut. It divides the vertices in two. So this is S's side. So S's side has S on it, and this vertex. And T's side has 4 vertices on it. So these 3 vertices, and then T. So this would be S, and this would be S complement. So our next definition is that we write E of S complement to denote the edges that start in S and end in S complement. So the thing I want to emphasize about this definition is that the edges have to start in S and end in S complement. So you can think of them as the edges that cross this divide, but the direction in which they cross the divide is important. So in terms of this example, there's only 2 edges that start in S and end in S complement. So that's this edge up here, and then this edge down here. And then this edge also crosses the divide, but it's going in the wrong direction. So it doesn't count in this E from S to S complement because it doesn't start in S and end in S complement. So our next definition is that the capacity of an ST cut is the following. So we're going to denote that as U of the cut, which is just the sum over all edges that start in S and end in S complement of the capacity of that edge. So just rewriting this mathematical definition in English is just the sum of capacities of edges starting in S and ending in S complement. And the last definition that we'll have is the residual capacity of an ST cut, which we'll just denote as R of the cut is equal to the sum over all edges in the cut of, now we're just going to sum up their residual capacities as opposed to their original capacities. So intuitively, this mathematical formula just is the sum of residual capacities of edges starting in S and ending in S complement. So edges from S to S complement. So just to illustrate these definitions in terms of this picture, the capacity of this ST cut would be just the sum of these two edges that start in S and end in S complement. So let's see why we're discussing these definitions of ST cuts, etc. Imagine I have a graph here, and here is S, and here is T. And there's some kind of cut dividing S from T. So here's a cut dividing S from T. And suppose the capacity of the cut is 40. So that means that the sum of all of the capacities of these edges going from S side to T side is 40. If somebody comes along and tells you that they can move 50 trucks from S to T, you shouldn't believe them. And that's because any truck that moves from S to T has to cross this divide. And these are the only edges that allow you to cross the divide. And so that means that the total number of trucks I can move to S from S to T has to be less than or equal to 40. So that's kind of a little statement we can make here, that the max flow has to always be less than or equal to the capacity of any ST cut. So if somebody comes along and gives you the capacity of a ST cut, I immediately know that that's an upper bound on the maximum number of trucks I can move from S to T. And what gives me the best upper bound, which is going to be the smallest upper bound here, is going to be the ST cut that has the minimum capacity. So I know that the max flow is less than or equal to what we're going to call the minimum cut. So this you can just think of as the capacity of the minimum capacity ST cut. So this is kind of the best upper bound we can get. But a natural question to ask is, suppose that the minimum cut, this kind of most constraining choke point from S to T, suppose that the minimum cut is equal to 40. Does that mean that we can actually move 40 trucks from S to T? It's not entirely clear whether we can actually move these 40 trucks or not. It may be that something is going on in the graph that doesn't allow us to move 40 trucks. So let's see if there's a way that we can guarantee ourselves that if the minimum cut is 40, then for a fact we know that we can move 40 trucks. And to see that, we really have to take a look at the dual of this LP. So let's write down the max flow LP. It looks something like this. So we had to maximize, and our variables were v and y. So we're trying to maximize v such that the sum of all y's going into S minus all y's going out of S was equal to minus v. We had a similar equation for t, so everything coming into t, everything going out of t is equal to v. Then for all other nodes, the right-hand side was 0, so this is for all a not equal to s, a not equal to t. And then we had some capacity constraints. So for each edge, we knew that we couldn't send more trucks on the edge than this capacity uij. So this is for all ij in E. And then the yij is we need it to be bigger than or equal to 0. So that's our max flow LP. And now let's take its dual to see what that looks like. And to take the dual, we have to introduce some dual variables. So here's some dual variables on this constraint for the s's. So that would be a row s. Let's just call that variable row. So this is the constraint for the t node, that the trucks coming in minus the trucks coming out has to be equal to v. So let's call that variable row t. And then there's a bunch of constraints here, one for every node other than s and t. And we're just going to call those row a's. We also have these capacity constraints, and we have to introduce some variables for the capacity constraints. So let's call those pi ij's. And just to be clear on why I called these variables what they are, there's kind of one of these network flow constraints for every node. And that's why the subscript here is just a node. And there's one constraint here for every edge. So that's why these pi ij's, there's one for every edge in the network. So now let's here write the dual of max flow. So this dual, since the primal was a maximum, is clearly going to be a minimum. And it's going to be a minimum over these dual variables. So a minimum over the rows and the pi's. Now let's write down the objective function here. So the objective function is going to be the constants times the dual variables. But this v here, it isn't a constant. It's actually a variable. So we wrote it on the right-hand side, but it actually, since it's a variable, it should have been over on the other side of this equation. So the constant in this equation is actually 0. So we have a 0 times this row, plus another 0 times this row, plus a bunch of zeros times all of these rows. So the rows don't actually appear in this objective function. So let's see about the pi's. So the constant in this equation is this capacity uij. So over here we should have a sum over all edges ij of the uij times pi ij. So now let's write down the constraints of the dual. So the constraints are going to come from the variables in the primal. So there's going to be one constraint for each of the y variables. So that's the yij constraints. And we're going to have one constraint for this v variable. So the v variable is slightly easier, so let's start with that. So the right-hand side of this constraint just gets determined by the coefficient of the v variable in the objective function. So that's why the right-hand side is just going to be equal to 1, because the coefficient of v here is 1. And then let's leave the inequality here for a second. And let's write down the left-hand side. So the left-hand side gets determined by the coefficient of v times the dual variable and all of the constraints that v appears in. So the coefficient of v here is actually positive 1, because when we move v to the appropriate side, its coefficient is going to be positive 1. So we get positive 1 times rho s, so that's just going to give us a rho s. And the coefficient of v in this t constraint is going to be negative 1, so we get minus rho t. Now, the inequality sign here gets determined by whether v is a positive variable, a negative variable, or an unrestricted variable. And in this original linear program, v is unrestricted. So this constraint right here ends up being an equality, because unrestricted variables correspond to equality constraints. So let's do the same kind of deal for this y variable. The right-hand side here is going to be 0 because the coefficient in front of y in the objective is 0. So this right-hand side is just 0. Let's leave a box that we're going to fill in a moment for the constraint for y. And let's do the left-hand side. So yij corresponds to a particular edge that goes between two specific nodes, I and j. And this particular variable is involved in exactly 3 constraints. So one constraint that it's involved in is its capacity constraint. And its coefficient there is 1. So we get a plus pi ij out of that, because the coefficient here is 1 times this dual variable, which was the pi ij. But this yij variable also appears in the network flow constraint for I and in the network flow constraint for j. So in the network flow constraint for I, this arc ij is leaving node I, so its coefficient of yij is going to be a minus 1. So that's why we get a minus rho I. So that's the minus 1 in front of the yij times the dual variable of that network flow constraint for node I. So that's why we get a minus rho I. And then a plus rho j that comes from the network flow constraint for node j, because the arc is entering j. So that gives us this left-hand side of the constraint. And now this inequality here, you can just figure out from your dual cheat sheets. So we're going from a maximization to the minimization, and the original variable was bigger than or equal to 0, so that means that the constraint has to go like this. Okay, so now we figured out the 2 constraints on the dual of the max flow, but let's also figure out what the variables should be. So let's see if the rows, should they be unrestricted, positive, or negative? Well, the rows correspond to equality constraint, so that means that the rows are unrestricted. So what about the pi's? So the pi's correspond to less than or equal constraints, which means that they have to be bigger than or equal to 0. So that now gave us an objective function and 2 constraints for the dual, and then we also know each of the variables, whether they are unrestricted or positive, etc. So now we have the dual of the max flow LP, but let's spend a little bit of time trying to interpret exactly what that means, or what's the meaning of all of these variables. So let's begin by just considering this constraint right here. It just says that the difference between rho s and rho t has to be 1. And we know that the rows are unrestricted. So let's just say that we're going to set rho s equal to 1, and we're going to set rho t equal to 0, because that makes their difference equal to 1. And over here, let's kind of get a picture of what that looks like. So here's node s, here's node t. Here's some other nodes in between, maybe. So A, B, maybe a few other nodes. And we're saying that rho s we're going to set equal to 1, and rho t we're going to set equal to 0. So then let's take a look at this objective function. We'd like to get this objective function to be as small as possible, but the pi's we know are bigger than or equal to 0, which tells us that the smallest this objective function could get is 0. Because these constants in front of the pi's, the capacity constants, they're all positive. And so the smallest we could hope for in this objective is 0, and we would get that by setting the pi's to be equal to 0. So let's see if we can actually set all of those pi's to 0 or not. In particular, this edge from S to A has some pi associated with it. So let's see if we can set that pi to 0. And what could potentially stop us is the one constraint that the pi is involved in. So this constraint for this particular edge looks like this: minus rho s plus rho a plus pi sa has to be bigger than or equal to 0. So all I did there was substituted the particular S to A edge into this constraint. So it starts at S, it ends at A. So that's what we get: minus rho s plus rho a plus pi sa. Now we know that rho s is 1, so I know that this first term is minus 1. I haven't decided what rho a is going to be yet, and I haven't decided what pi sa is going to be yet. But I know that this has to be bigger than or equal to 0. And I know I'd like to set the pi's to be equal to 0 if I can. So let's imagine that I set the pi equal to 0 here. But if I set the pi equal to 0, that means I have to set rho a equal to 1 also to satisfy this constraint. So let's say that here we set rho a equal to 1. But similar reasoning for this next edge from A to B tells me that I either have to set the pi for this edge equal to 1, or I have to set rho b equal to 1. So let's imagine that we set rho b equal to 1. And then let's follow an imaginary path that starts at S and goes all the way over to T. So I set the rho at S to 1, I set the rho at A to 1, the rho at B to 1, and so forth and so forth. But eventually I have to start setting the rows to 0, because rho t is equal to 0. So at some point right here, there's going to be some edge where its starting node is going to have a rho equal to 1, and its ending node is going to have a rho equal to 0, which means that its pi has to be equal to 1. So this edge is kind of crossing between a 1 label and a 0 label on a node. And when it does that, we have to pay the penalty for the edge. The penalty being this objective constant, the uij's. And so since I have to pay for an edge on a path from S to T, what I'd like to do is kind of pay for the minimum cost edges. So just the edges that divide S from T, but do so in a way that minimizes the sum of their capacities. And so the punchline of this whole discussion is the fact that this LP right here is a minimum cost LP. So in particular, it's a minimum cost LP because the rows specify which side. Of course, I mean not minimum cost LP. It's a minimum cut LP. So it's asking for a linear program that's asking us to separate S and T in such a way that we get the minimum cut between S and T. So the rows specify which side of the cut a node is on. So in particular, if a row is equal to 1, it's S's side. And if rho is equal to 0, it's T's side. And the pi's specify edges crossing from S's side to T's side. So in particular, it's going to be 1 for edges that cross, and 0 otherwise. So it's going to be exactly these edges that cross from S's side to T's side that we have to pay the Uij penalty for. So now we have just a very good understanding of the relationship between max flow and minimum cut. In particular, max flow and minimum cut are duals of each other. And so originally, we had said that the max flow has to be less than or equal to the minimum cut. So that was just this intuitive idea that anything that we send from S to T has to go through the cut, and so the cut gives us an upper bound. But we had a question, does max flow, is that actually equal to the minimum cut? And now we can answer this question, yes. The max flow actually is equal to the minimum cut. And the reason for this is strong duality. Because max flow and min cut are duals of each other, we know that their objective function values have to be equal. So the maximum flow value is equal to the minimum cut value. And this result for this particular network application is often referred to as the max flow min cut theorem. It just says that the maximum flow value is equal to the minimum cut value. And by the way, this original result, the intuitive upper bound that max flow is less than or equal to min cut, this is just weak duality. So really, these two problems of max flow and min cut, in some sense, they're the same problem because they're duals of each other. So if you have an answer to one, you can very easily get the answer to the other. And so we're going to see that in terms of our algorithms very shortly, probably next lecture. But so now that we have a bit more of an understanding of how max flow works, let's take a look at how an algorithm for solving max flow might work. So suppose that somebody comes along to us and shows us this network. So 2, 1, and 3. So this is the network, and this person who showed us the network would like us to move as many trucks from S to T as possible. So to do this, a natural thing to do is first find a path from S to T. So suppose that the path we find is this path, S0T. So how many trucks can we move on this path, S0T? Well, it's equal to the minimum capacity of an edge on the path. So add as many trucks on the path as the smallest capacity edge. As soon as we start adding trucks to this network, we no longer should be looking at the capacities of these edges, because now there's some trucks over there, and so even though this says capacity 4, maybe we have no capacity left for moving more trucks along that edge. And so we should really be looking at the residual network from here on. So for this particular example, the residual network looks something like this. So on this edge from S to 0, we have no capacity left because we've put all the 4 trucks that we can. But from 0 to S, we have some residual capacity of 4. And this corresponds to backing off on the 4 trucks that we're sending in this direction. From 0 to t, we have a residual capacity of 1 because we still have the ability of putting 1 more truck over there. And from t to 0, we have a residual capacity of 4 that corresponds to the ability to back off on the 4 trucks that we're sending in that direction. Now, the other 3 edges, we didn't touch them in terms of adding trucks. And so those other 3 edges look exactly the same as they do now. So there's a 3 here, a 2 here, and a 1 here. So this is what the residual network looks like. And so the next time that we're trying to increase the number of trucks that we're moving from S to T, we're going to find a path in the residual network. So let's say in this particular network, we find the path S10T. For example. So how many trucks can we put on this path S10T? Well, we're going to add as many trucks as the minimum residual capacity of an edge. So the minimum residual capacity here is 1. So it's this 1 that's going to limit us from putting more trucks on along that path. So that's the basic idea. We're just going to keep repeating this. We're going to find a path. We're going to add more trucks to that path. We're going to look at the new residual. Going to see if we can add another path and so forth. And we're going to end when there's no more paths from S to T. So that describes the entire basic algorithm for max flows. And this algorithm is called the Ford-Fulkerson algorithm. So it takes in as an input a graph G and 2 nodes S and T. And at the beginning of the algorithm, we're just going to set all the Yij's equal to 0. So all this means is that we're going to start with an empty trucking plan. So a trucking plan where nothing is moving anywhere in the graph. And then while the residual graph G of Y has a path from S to T, we're going to do the following. We're going to let P be a path from S to T. In this residual graph. And we're going to let delta be the minimum over all edges in that path of the residual capacity of that edge. So just in English, this is just the minimum residual capacity on P. And we're going to add delta units of flow on P and update Y and G of Y. So that's the basic idea of this algorithm, and we're going to keep repeating it until we can no longer add a path from, or find a path from S to T. So for today, we're not going to be able to look at an example of this algorithm. So we're going to do that first thing next time in class. But there we'll be able to see how when we add some amount of flow on a particular path, that really is going to update this residual graph right here. And it turns out that you don't really have to maintain this vector y. Just knowing the residual graph and the original graph allows you to reconstruct what the flows are. But we'll see more of that tomorrow. So that concludes class for today. Thanks a lot for listening, and I'll see you all next time.